HOD Professor Nikki Chaturvedi sir, my seminar guide Sandeep Parashar sir, seminar coordinator DB Sharma sir, faculty members, examiners, and my batchmates. I am Utkarsh Nagar, pursuing my BTech from University Department of Mechanical Engineering, Rajasthan Technical University, Kota, Rajasthan. Introduction. What is thrust vectoring? Thrust vectoring is the ability of an aircraft or other vehicle to deflect the angle of thrust away from the vehicle's longitudinal axis. Thrust vectoring involves redirecting some portion of thrust from jet engine in any direction other than the normal axial direction. Thrust vectoring is used to control an aircraft's or rocket's motion in roll, pitch, and yaw. Figure 1 represents thrust animation in rocket. Figure 2 demonstrates the modern EJ200 engine system installed in Eurofighter Typhoon aircraft. Historical perspective. Origin. The thrust vectoring control history first came from rockets. The evolution of rocket has made it an indispensable tool of exploration of space. In rocketry and ballistic missiles that fly outside the atmosphere, aerodynamic control surfaces are ineffective. So thrust vectoring is the primary means of attitude control. For aircraft, the method was originally envisaged to provide upward vertical thrust as a means to give aircraft vertical or short takeoff and landing ability. Evolution. The Germans used graphic control vanes in the exhaust stream of their V2 ballistic missiles in World War II for directional control. Figure 3 depicts graphic thrust vectoring vanes which were used on German V2 rockets. The Hawker Siddeley Harrier in the British aircraft, the first vertical and short takeoff and landing jet fighter bomber. Figure 4 is the Harrier fighter, including the detail of the jet orienting nozzle. The F-35B Lightning II 2006 features a vertical lift fan and pivoting engine nozzle to deliver vertical landing and short takeoff capability to expeditionary airfields. Figure 5 is an illustration of thrust vector control techniques used on the F-35B. Advantages of thrust vectoring. Agility. A requirement of modern warfare is the improvement of maneuverability and control capabilities which thrust vector control provides. The agility of aircraft can be determined by such things as pitch, roll, yaw rates, acceleration, deceleration, and turning ability. Short takeoff and landing. Aircraft that have vertical and small takeoff and landing zones are largely advantageous as it reduces the space required for operation of aircraft. Fuel consumption, flight range. An aircraft with thrust vector control requires less thrust to achieve desired results, such flight regimes as cruise, climb, and descent. This has effect. It reduces the fuel consumption of the aircraft due to the lower thrust requirement, which in turn increases the aircraft's flight range. Still, thrust vector can supplement control surfaces. The benefit of reduced dependence on control surfaces are reduced drag, reduced aircraft weight. It has been shown that thrust vectoring has the ability to provide tailless aircraft. Figure 6 is depicting F-35B vertical takeoff and landing capability. Figure 7 showing a MiG-29 post-stall maneuvering. Methods for thrust vectoring. Several thrust vector control methods are available for use on a jet engine. Some of these options include rotation of the entire engine relative to the vehicle, rotation of the engine nozzle in order to direct the exhaust gases in a different direction, insertion of movable vanes or paddles into the exhaust flow, secondary fluid injection, diversion of exhaust gases. These methods fall into three primary categories: nozzle manipulation, secondary fluidic injection, and exhaust gas deflection. Mechanical nozzle manipulation. One commonly used thrust vectoring method involves manipulating the physical configuration of the exhaust nozzle on the jet engine or rocket motor. This method is commonly used on aircraft and is most common method used with rocket-propelled launch vehicles. Gimbaled thrust is the system of thrust vectoring used in most rockets, including the Saturn V lunar rocket and Falcon 9. Figure 8 is the schematics of mechanical engine steering. Secondary fluidic injection. Fluidic systems use momentum injection or removal to vector the exhaust stream towards a reaction surface. Mechanical thrust vector control systems are effective and efficient in terms of force and moment generation. However, they can be complex, heavy, difficult to integrate, and aerodynamically inefficient. In contrast, fluidic systems are lightweight, simple, and relatively inexpensive. Figure 9 is the schematic diagram showing throat shifting fluidic thrust vectoring technique. Exhaust vanes. An alternative to nozzle manipulation is direct flow manipulation by use of post-nozzle exit vanes or pedals. One of the earliest methods of thrust vectoring in rocket engine was to place vanes in the engine exhaust stream. These exhaust vanes or jet vanes allow the thrust to be deflected without moving any parts of the engine, but reduce the rocket's efficiency. Figure 10 is NASA's F-18 HAL demonstrating thrust vectoring achieved using movable pedals. Figure 11 is the X-31 and it's the of movable pedals mounted in the engine's exhaust. 2D and 3D thrust vectoring. An aircraft traditionally has 3 degrees of freedom in aerodynamic maneuverability: pitch, yaw, and roll. The number of dimensions of thrust vectoring relates directly to how many degrees of freedom can be manipulated using only the vectored engine thrust. Therefore, 2D vectoring allows control over 2 degrees of freedom, typically pitch plus either roll or yaw, while 3D controls all 3. Figure 12 depicts vehicle's degrees of freedom in aerodynamic maneuverability. Operational examples: rockets. The engine of Saturn V, all 3 stages, were mounted to the aft end of their stages by universal type ball and socket joint. Figure 13 is the ground level view of Apollo 11 Saturn V. Japanese M5 space launch vehicle cannot alter the direction of thrust fuel, so they instead inject a cooling fluid along one side of the exhaust nozzle that forces hot gases to exit on the opposite side to provide a vectoring effect. Figure 14 is the Japanese M5 space launch vehicle. Aircrafts. The Lockheed Martin F-22 Raptor is an all-weather stealth tactical fighter aircraft having radar cross-section of 0.0001 square meters. Figure 15 is the Lockheed Martin F-22 Raptor. The Boeing C-17 Globemaster uses this technology to provide a medium short takeoff and landing capability. Figure 16 is the Boeing C-17 Globemaster. Missiles. The AIM-9 Sidewinder is a short-range air-to-air missile of the US Air Force. The AIM-9 is one of the oldest, lowest-cost and most successful air-to-air missile, with an estimated 270 aircraft kills in its history of use. Figure 17 is the AIM-9 Sidewinder missile. The BrahMos is a medium-range stealth ramjet supersonic cruise missile, notably being the fastest supersonic cruise missile in the world. 2 main features of this missile are its cruciform wings and its thrust vectoring capability. Figure 18 is the BrahMos missile. Conclusion: the implementation of thrust vectoring can lead to a reduction in size or complete removal of aircraft control surfaces. This has potential benefit of reducing overall aircraft weight, drag, and radar cross-section signature. Mechanical thrust vector control systems are effective and efficient in terms of force and moment generation. However, they can be heavy, complex, difficult to integrate, and aerodynamically inefficient. So, fluidic systems are lightweight, simple, and relatively inexpensive. The main challenge with fluidic system is in creating an effective and efficient system with acceptable control response characteristics. References: these are the papers and material which helped in successful completion of this presentation. Thank you.